Greetings to everyone. Today we are from Group 6 and we are going to present our topic, the wave propagation in a medium. The objective of the experiment is to determine the dielectric properties of solid materials based on shifting phase of RF transmission wave using rectangular waveguides. The experiment is conducted in the radar lab in UTM.
Hello, I am Wan Muhammad Irfan bin Wan Muhammad Fauzila and I will cover the theoretical parts. First of all, I will briefly explain about waves. Waves can be defined as any disturbances or vibrations that move from one point to another and will carry energy in its movement. The term wave propagation refers to the movement of the waves in regard to its way of travel. Another relevant thing to note is about medium, which will act as the energy carrier for the waves to propagate through. It can be either solids, liquids or gases. That is not the case for all waves, as some doesn't need any medium to propagate as they can do so through air. Now we will move on to the specific of the experiment. Usually for material characteristic, we can study the relative permittivity, relative permeability and the conductivity, but for this one we will focus on the relative permittivity. In theory, a plane wave is partially reflected and partially transmitted when it encounters a different medium. The mentioned parameters will affect the reflection and transmission of waves, so we can demonstrate and use the concept of wave propagation through medium to obtain the relevant information needed. For this experiment, a network analyzer is needed, where it will give an overview of what is happening on the network by allowing users to look at the actual data that travels over it packet by packet. The network analyzer will be used to measure the phase and amplitude of both the waves, like the reflected waves at the receiver and incident waves at the source at the different ports. The network analyzer operates in scattering parameter, which is the input-output relationship between ports. For this experiment, the observed parameters are the S21 and S11. Next, I have listed the formula used to calculate the desired parameters with reference to Dr. Yu Kok Yao. The formula utilized the result obtained from the experiment to get the permittivity of the medium. That's all from me. Thank you.
To conduct the experiment, we will need a few apparatus and material. First, we will need one Fork factor network analyzer, two coaxial cables, two rectangular waveguide adapter, and one waveguide spacer with wave aperture 0.0348, and 4 samples will be Teflon, FR4, acrylic, and PVC, and lastly, an N-type calibration kit. Firstly, the experiment is set up as shown below. Connect the coaxial cables to the network analyzer and the rectangular waveguide adapter. Then, both waveguide apertures is calibrated using TRL method, which is true, reflect, and light. Then, before we measure any samples, after the calibration, the empty waveguide spacer is placed and screwed at the center of two waveguide adapters. Then, the magnitude phase shift of transmission coefficient from 6 GHz to 8 GHz is measured and recorded in table 1. Then, step 3 and 4 is repeated by replacing the Teflon sample into the waveguide spacer. The attenuation constant, which is alpha, for the sample is calculated and recorded the calculated value of alpha in table 2. Then, the dielectric constant, loss factor, of the sample is measured and also recorded. Lastly, step 5 and 6 is repeated by replacing sample to FR4, acrylic, and PVC.
I'm Yeong Di Wei. I'm going to present the finding part of this assignment. It's split to two sections, which are data analysis and difference between experimental results and reference values. We tabulated the data obtained in the experiment. We have used 5 different samples, which are air, empty field, acrylic, Teflon, FR4, and PVC. The parameters tabulated are linear magnetic of reflection coefficient S11, linear magnetic of transmission coefficient S21, phase shift of transmission coefficient V21 in radian, and propagation constant of free space K0 for frequency range 6 GHz to 8 GHz. The propagation constant of free space K0 can be calculated using this formula 2.FOC. After that, we analyze the data by using Microsoft Excel with these 3 formulas to calculate the attenuation constant, dielectric constant, and loss factor. The other 2 parameters used in calculation, which are width aperture of the rectangular waveguide and thickness of the sample material, are 0.034 meter and 0.007 meter respectively. These are the results we found. Moving on, we calculated the difference between the experimental results and reference values for the frequency range 6 GHz to 8 GHz and the average percentage error. The average percentage error for sample acrylic, Teflon, FR4, and PVC are 5.79, 8.49, 16.68, and 6.86 respectively. It's noticed that the average percentage error for FR4 is large due to the percentage errors at frequency 7.9 GHz and 8 GHz. It might be due to the phase shift ambiguity in microwave permittivity measurement. It occurs when the thickness of the sample material is greater than lambda/4 of the total propagation wavelength. We can solve this by selecting a sample material with a proportionate thickness. That's all from me. Thank you.
In conclusion, from this experiment, we have learned that the relative permittivity has a complex component, which the real part referring to the dielectric constants, while the imaginary part refers to the dielectric loss factor. From this experiment, the relative permittivity of the acrylic is 2.83 with percentage error of 5.79%. The relative permittivity of Teflon is 2.23 with percentage error of 8.49%. And the relative permittivity of FR4 is 5.08 with percentage error of 16.68%. And the relative permittivity of PVC is 3.1 with percentage error of 6.86%. Other than that, in this experiment, we also learn how to use a network analyzer to obtain the magnitude S21 and phase shift V21 transmission coefficients. That's all from us. Thank you.